one of the first things we did after we discovered that there was a thing called a resistor, such that the ratio of the voltage across it to the current through it is always constant. We call that the resistance. Is we asked what happens if we put two of them in parallel or multiple, if we put many of them in series or many of them in parallel. That's the next thing we asked in chapter 19. What happens if we put them in series? What happens if we put them in parallel? We have this new thing now, this new sort of circuit element. We can call it a capacitor. It is a thing that has a capacitance. The symbol we use for it is two lines next to each other, kind of like a battery, but that are the same length. Because once we charge up, sorry, emphasis there was wrong. Once we charge up a capacitor, we can take everything else away and those two plates stay charged. We could connect them like a battery and that charge would flow through whatever circuit we set up. So it makes sense, I think, to use a similar symbol, but it's not quite a battery because it's not an electrochemical thing. We have to spend energy to charge it up first. All right, so the question is, what is the equivalent capacitance of two capacitors in parallel? And then what is the equivalent capacitance of multiple capacitors in series? Well, I guess two or more capacitors, but I like two. Okay, here's the story though. The battery is doing a good job of setting up an electric potential difference between this point and this point. But these are wires. This point is electrically the same as this point because the wire has, we assume, no resistance. There's no electrical potential difference between that point and that point. And which means if we follow the wires, there's no electrical potential difference between this point and this point. Because it's just wires between them. And frankly, there's no potential difference between that point and that point. And if we track this point, there's no difference between this point and follow it along this point or this point. They're on the right-hand side of the thing. This point and this point and this point are all at the same electric potential. So we take our voltmeter, our 2 voltmeter leads, and we measure the potential difference across the battery. That is exactly the same as taking our 2 voltmeter leads and measuring the potential difference across the capacitor, because that's the same. It's the same voltage, it's the same potential difference. Maybe one's positive or negative, okay, but it's the same size. It's the same magnitude potential difference because they're the same points in the circuit. Actually, it shouldn't even be negative. Check it out. The battery wants to put positive charge here on this side of capacitor 2 by taking positive charge away from this side, leaving this side negative, just like the battery. So the left-hand side of this capacitor is going to be positive, and the right-hand side is going to be negative, just like the battery. We take our 2 voltmeter leads, move them from here to here, nothing changes. It's exactly the same potential difference. So how much charge is on it? All right, well, Q, we said, was capacitance times potential difference, but that's just the battery. I'm just going to leave it as V. V battery. That's the charge on capacitor 2. Exactly the same logic lets us talk about the charge on capacitor 1. All right. So what is the effective Capacitance? Well, let's think about this. We had to move from this side through the battery to this side. We had to move enough charge that we could put this much on one plate and this much on the other plate. So we had to move the total because charge is conserved. If we put this much here and this much here, it's the total that we need. Okay, so the total charge, Q equals Q1 plus Q2. It's sort of like saying how the current needs to add in a junction. We've got charge Q going this way, Q1, I guess, and charge Q2 going this way. They need to come from somewhere, and they all needed to come from here, and that means we're moving a total charge equal to the sum through the battery to get it up here. All right, so the capacitance, the equivalent capacitance, is the total charge we're moving, Q, divided by the potential difference we used to do it. Q is Q1 plus Q2 divided by the battery. Q1 is given by that, Q2 is given by that, C1, the battery, C2, the battery, all divided by C1 plus C2. The effective, the equivalent capacitance of capacitors in parallel is just the sum. Same kind of deal like resistors in series, which is interesting. And it makes me wonder if it's going to flip fully. Resistors in series are like capacitors in parallel. Are resistors in parallel like capacitors in series? Let's find out. Good with that? Summarize the results. Equivalent capacitance is just the sum of the individual capacitances. And the sigma expression, add them all up. All right, what about this one? A battery this strong means that we can move charge. We can take and put a total positive charge Q here by moving it from here, so we have a net negative on this side. These inner pieces aren't actually part of the circuit. This wire comes around from the battery, gets to this plate, and then there's a gap. Maybe that gap is filled with a dielectric, one of these other materials than free space. But what if it's just free space? This is vacuum in here. There's no circuit connection. There's no wire between this point and this point. We can't just take extra charges from here. We're stuck. If the battery is strong enough to put a charge Q here, that's the end of it. But this all is still conductive. And that means that we can get an induced charge. this positive charge here pushes the positive charge away from it, pushes the positive charge in this segment as far away from it as it can get, all the way to the next plate, leaving an induced negative Q on the close plate. And then the same thing happens. This positive charge here pushes the positive charge away over there. Well, and this minus Q here is attracting the positive charge, which leaves us with a negative charge on this inside plate here. So each capacitor now has the same magnitude Q on each of its plates. And that's sort of like how in series, the current is the same everywhere. Right? Here we said the current, the charge has to split and be accounted for on both pieces according to the total charge that we can move through the battery. Here, whatever current we're drawing, whatever current is moving in the circuit, it's got to be the same all the way through because this is a series arrangement. But if we're moving current, we're moving charge. And that means the charge that we put, the charge that we move, it has to be the charge that we move in all the parts of the circuit. Otherwise, we're breaking the, breaking conservation of charge again. What potential difference do we set up on each of these capacitors? Well, potential difference, C is Q over, hey, by the way, if you haven't seen this trick before, it's worth looking at. Capacitance is the ratio of charge to potential difference. Which one do you want to solve for? Q, capacitance times voltage. You want to solve for voltage instead? Q over C. As long as you put them in the right order to begin with, that trick will work. Okay, Q over C. So the potential difference across capacitor 1, the charge, and the capacitance. Now the charge is all the same, so I'm just going to call it Q. That's the story. The potential difference across capacitor 2 is that same charge over capacitance 2. The potential difference across capacitor 3 is that same charge over the other capacitance. All right, cool. But this is a series circuit. In order for energy to be conserved, the potential difference that we encounter through the battery needs to be accounted for on our way back through the capacitors. Imagine we're walking this circuit, like we go from a plus Q, hop over the gap to a minus Q. That's a decrease in electric potential. And then we do that again, there's another decrease in electric potential. And we do that again, there's another decrease in electric potential. So the combination, capital V, of the battery has to be equal to, in magnitude, the potential differences across the 3 capacitors. Because we go up this much, we got to go down that much. All right, now the voltage across the battery, we have seen that the voltage of the battery allows us to move an amount of charge, Q, and store it in a capacitive arrangement like this according to the capacitance of the arrangement. We have moved from one side to the other, Q. We move, how much charge did we move through the battery to take from here and put there? Q. What capacitance are we talking about? What's the equivalent capacitance? The voltages have these expressions: Q over C1 plus Q over C2 plus Q over C3. And yep, you got it. We've got the same, cancel the Q everywhere. We've got the same reciprocal relationship for capacitors in series that we did for resistors in parallel. It's pretty cool. So this is for series. For parallel, the equivalent capacitance in parallel. So series equals the, I'm going to write it this way. The reciprocal, 1 over the sum of the reciprocal capacitances. And even you could write it with another negative exponent, just to keep the expression really clean. Ci to the -1. Take each capacitance, find 1 over that, add all the results. Find that sum, that's this side, and we still have another 1 over thing to straighten out. That's this exponent. It's just a different way to write the formula that you know. The equivalent 1 over the equivalent capacitance is the sum of 1 over the individual capacitances. Cool. We are moving right along. That's the second segment. There's only one more.